with some econometric.
Yeah.
Great. So you decided that you had 45 minutes.
Yeah, 45 minutes is perfect. Always happy to talk about this stuff during break. This is a project which is basically right now at the 40% point. So when I first met Philippe in the summer CA meetings, I was actually remotivated to do this work. Then when he invited me to this conference, I suddenly had a deadline. But as I'm going to make clear, the reason why I didn't get to where I want to get to is going to lead to a lot of the theme of this talk, which is the science and how we're coming up with genetic associations and how we're creating things like polygenic scores, which Mike talked about at the end of his talk. It's really kind of sketchy, is a nice way to put it. So this is joint work with my colleague at Queen's Wei Li Ding and Jenna Lukanova, who is my postdoc at NYU Shanghai. And Jenny is doing all the data analysis, but I don't have numbers to show you, but I'll tell you what we're doing, and I'm happy to take questions. Regular economics rules, you can interrupt as often as you like, as rudely as you like. I don't take offense. I'm used to it. Okay, so I'm using the wrong button.
My first comment is that why don't you have your nice Tintin shirt? The one you had.
Oh, because I've gotten bigger after eating food in Montreal, so it's a little too tight. It's a little too tight now, okay, but okay. So a bit of motivation for this. So just, I guess a couple of months ago, I just opened up Cardiology Today. I was at a doctor's office just for a family member, and Cardiology Today had an article about what were the 10 most read articles in the top journal in their field. And what I just wanted to make clear about what the top 10 articles are, they all have genetics somewhere involved, which is sort of shocking. And what these genetic risk scores are was actually in 4 of them. What specific genes are was only in a couple of them. And then there's a couple of things which are about gene-environment interactions. So there's lots and lots of interest in doing research with this. You talk to people in the genetics community, they don't really they don't really run the numbers. It's mostly coming from statistical geneticists, and they're really working in an area where economists not only have absolute advantage, but comparative advantage. And just like we're losing a lot of space in the data science world, I think we should basically come back and reclaim our space. And I'm going to try to make a case about some of the things that they're doing and why we should be concerned. But the punchline, I'll give you the punchline already, it's that the way that these things are sort of run, it's with canned software. And people are very good at putting things into canned software and taking it out, but they have no idea what the canned software is doing. And once you start looking under the hood, you'll get quite mad, or I get mad. So what is a polygenic score? So I'm going to tell you that what a polygenic score is depends on what article you read, because there's very good definitions for a polygenic score, one of which Mike put up yesterday, and they're all used interchangeably, and I'm going to make a case about, I don't think any of them are really the right way of thinking about things. But the basic idea is that they're basically going to be a score based on, according to your genetic profile, how likely you are to have a certain disease, be it cancer, be it heart disease. And the basic idea is for personalized medicine is, if we know who's at high risk, then we can basically come up with different treatment plans. This is the whole hope of this stuff. At the far extreme, you have now companies, this is where the big money is coming in, who are basically offering online, if they could just do a little swab of you, they could tell you your risks, and they have these very, very fancy proprietary algorithms and a whole bunch of things, and this could be really, really important for you. So there's lots and lots of companies on that side trying to talk about how these polygenic scores can inform consumers. I don't think that there's much evidence about exactly how well these things perform. There's lots of claims. From an economist's point of view, these scores are basically things that are estimated, so they have lots of estimation error, and they're now becoming available in lots of data sets. So if you want to use the AdHealth data set or the HRS, there's polygenic scores in them. The thing is, if you actually want to understand what the polygenic scores are doing or how they're calculated, there's no real documentation, and this is where I'm sort of trying to do a bit of work on right now. The other big area for the dollars, and this is where I don't want to steal too much of Amitabh's thunder in, I guess, 90 minutes or so, is that there's a lot of drug development that's tied to specific genes. And one thing that we know is, and the basic idea here is that if someone, we're basically going to try to come up with we might have a disorder like inherited retinal diseases. If you have this RPI 65 gene and you have one of the 2 minor alleles, there's now a drug out there called Luxturna that if you can basically, you use it, the chance of a cure is about 90%. And and this is something which I'm sure he's going to talk a lot more about, is that because it's so highly effective, the pharmaceutical company has and is interested in doing this. They're basically doing lots and lots of innovation tied towards genetic markers. The big question, though, is from a health policy standpoint, is that one of the goals from a health or a public health system is we want basically people to have good health. We also want people to be wealthy. We also want equity. And you can't get all three at once. And you sort of have this dilemma here is that nowadays, if you actually look, going back to July 2018, there's apparently 701 gene therapy trials going on in the US at various different stages. So the role of genetic markers at influencing pharmaceutical development is enormous, as well as the fact that people are using lots of information about genetic markers to come up with new products to sell to consumers. And the whole hope is that this will improve health and healthcare. All of this is relying on is how good is that information, how good is that evidence. Some of the evidence is fantastic. In this case, we have a disorder which is strictly caused by one specific gene. We know fantastic. Lots of other things that we're interested in. The evidence is quite murky. So anyone who looks at my Vita knows that I like to jump around between topics, and what really got me interested in genetics is, what usually gets me interested into most topics is, there's a new cool data set out there and I get to start to play with it. And I like always to play with new data sets. I'm not a big fan of writing up the paper, but I like to play with the new data. And there's now all this new data that's coming online with lots and lots of polygenic scores. And I am now seeing a lot of these things crossing my desk to take a look at and comment on. When I first got into genetics, the way I thought about using genetic markers was, as labor economist, wearing my labor economist hat, this is a way to talk about permanent unobserved heterogeneity. Why do two different people have different things? We don't have really good measures on ability or motivation, but maybe we can use this information about genetic markers to learn more about types of people, or we could group them. This is how I started to get into this. I think where the literature has sort of moved is that people are now treating this information in a very, very different way. And I'm going to talk a little bit about it. I will say, and this is something that I just mentioned before, the way people talk about different terms, like what is a polygenic score, as I'm going to show you in about 5 or 6 slides, depends on what paper you read. These terms are used interchangeably, and I think that there's a lot of room. And one of the big things that I'm going to be pushing on is that we know a lot of things in microeconometrics and economics, and we know a lot about how health is produced. We have models going back to Grossman all the way forward. We should be using that information to model some of these outcomes that are being studied. And I'm going to talk a little bit about this. The other thing that I'm going to point out is, I told you that my head is all over the place. So in 2015, I was asked to write a survey chapter. And at that time when I wrote that survey chapter, I basically said that researchers should shift away from specific candidate genes to polygenic risk scores. Since I wrote that survey chapter, I wrote 2 more survey chapters, and now my survey chapters say researchers should not use polygenic scores until they're well understood and shift back towards candidate genes. And I'm going to try to make that case why. And I think that this is going to be important, how we're going to be thinking about, so from the personalized medicine standpoint, I'm going to talk about how I would go about now analyzing data, but most of this talk is mostly going to be about contrasting these 2 different methods. So the first time I presented a variant of this talk, Dora Costa was in the audience and said, this is really, really interesting, but do you have any empirical numbers to show me what's going on? And this is one of the things that we've been trying to do is, we're getting data now from the Health and Retirement Survey where we have these polygenic scores, and I want to actually confirm whether or not some of the hypotheses that I'm going to say are actually right, or if I'm just worried for nothing. And what we're basically trying to do is decompose those polygenic scores into different parts. And you're going to see why shortly. I don't have anything. I don't have any numbers today, and a lot of it is because when we tried to rebuild the polygenic score with the raw data in the HRS, we couldn't get the same numbers that were in there for the polygenic score. And we've been spending now about 3 months going back and forth, not just with the people at the HRS, but the people who built the polygenic score for them, exactly what did they do. I'm pretty confident about what I'm going to talk about. The one thing which I think is very, very important to remember when people talk about genetics and genetic evidence, borrowing from Chuck Mansky, is really the incredible levels of certitude people have. People really make strong claims. And you're basically going to be creating things that are going to be estimated with big, big standard errors, and all that estimation error, all that random variation is going to be ignored. So what I sort of want you guys to become a bit more after this talk, hopefully, is to be a little bit more skeptical. I think that about what some of the claims are in the literature, about how sure we can be about any evidence we're getting from a study that's using genetic data to sort of inform either the development of polygenic scores or a product to talk about health risk. And I'll talk a little bit more about why. Okay, so as I said, the first time I presented this was at UCLA, and there's a very, very famous paper in the 1980s by Ed Lehrer called Let's Take the Con Out of Econometrics. So this paper was originally titled Let's Take the Con Out of Economic Applications. I hate the term economics. I don't think it's a special subfield. And what I'm mostly going to talk about is what is a polygenic score? Should you use it, or individual genetic markers? And individual genetic markers are called single nucleotide polymorphisms. Okay, so I'm just going to do like a 2-minute what is a gene review, just in case. So the human genome, you can think about it as a book. It's a book containing 3.2 billion letters. They're chemical letters, A, C, G, or T. Okay, the book contains 23 chapters. You can think about the chapters as the chromosomes. You get it at conception, one comes from your mother, one comes from the father, and there's a bit of random sorting. But genes that are located next to each other, they tend to be highly correlated. Those far away on the chromosome tend to be very, very different. Across this gene, every 1,200 to 1,500 letters, there's a difference between people. I have an A, she has a G. That's the difference. Those differences are going to be called single nucleotide polymorphisms. What a gene is a gene you can think about as a sentence. It's anywhere from about 200 to a couple of million chemical letters long. And what genes do is they build proteins. When you sequence the human genome, when it was originally done back in 2000, 2001, they did it letter by letter by letter by letter. Nowadays, that's very, very expensive to do, even with technology today. What's much cheaper to do is not to sequence the gene, but sequence the products the gene creates, like proteins. What genes do is they create proteins. If you have these small differences in your genetic code at one point versus another, the molecular mass of the protein differs. So most of the scans that are basically being used to get data on what is your genetic code, they're not looking at the full genome, they're only looking at what's called the exome, which is the protein amount, and at best they can tell you about 2% of the genes. But what they can do is they can use lots of information that, I know that this gene is located next to that gene, so on average, you probably have this gene over there. So there's a big, big challenge that lots of the data is really not actual, it's imputed. And this could be measured with error. Okay. What you should do, should you use polygenic scores or individual genetic markers to inform things? I think it's going to be really application dependent. I'm going to have a slide coming up where the answer that's on that slide, I typed up yesterday, but this morning I changed my mind on it. What is this polygenic score? You can think about it as one's risk of getting a disorder based on their genetic makeup, and there's 3 different ways it's calculated. Okay, so when I talked about this variation, there's these, every 1,200 letters, I might have A1, A1, Lee has A1, A2, Philippe has A2, A2. A2 is the most common one. And the question is, should I introduce these things as basically how many risk alleles I have, how many A1s I have? This is one way people do this. Another thing that people do is, maybe they should basically put these things in a series of dummy variables. One way that people estimate polygenic scores is they say, how many of the risky alleles do I have in my gene with no weights? So in this case, because I'm A1, A1, I have 2. Philippe is a 0 because he has A2, A2. We have variation across people when you do this over 1,000 genes. I have 970, Philippe has 940. What's the difference from going from 940 to 970? Is the marginal effect the same based on which binary allele we have? That's totally all assumed away. This is one way of doing it. The other way of doing it is they're going to basically run what's called a genome-wide association study. And this is like a massive regression with 3,000 variables. And they're going to conduct a prediction of basically you could think about the polygenic score, it's just a prediction using those 3,000 variables. You say, oh, those 3,000 variables doesn't sound that bad, except only 74 of them were statistically significant. So at the levels that we're going to use. So there's this big, big debate in this literature. Should a polygenic score use all your genetic information? Should it have equal weights or different weights? Or should it only have significant regressors or also insignificant regressors? One of the things which I'm doing in the paper is I'm basically trying to decompose a polygenic score into the components to tell you what's really driving the effects. That's what I wanted to show you today. I don't have the numbers yet because I can't even rebuild the number that's in there. So is everybody good on the 3 ways? Beautiful. What is a polygenic score in the language of economics? It's just a sufficient statistic. This is supposed to capture everything in our genetic data that's predicting our risk. That's it. Sometimes I wear a hat as an education economist or in economics education, and one of the things we do in economics education is we estimate education production functions. Just like in health economics, we estimate health production functions, and sometimes we put in lagged achievement or lagged health in that equation, and sufficient statistic to capture the full history of inputs, right? Because how good I do in Philippe's economics of information course is not just a function of how good a teacher he is, but it's also a function of how good my grade 10 math teacher was, my grade 4 math teacher. The full history matters. Getting all that data is hard, so I usually try to proxy it with just one variable that captures all historical inputs, and that is what the sufficient statistic is. This year was very, very popular in economics of education until the credibility revolution took off about 15, 20 years ago. Now people need to think of a clever identification strategy to talk about how some education input affects an output. So sufficient statistics were really not that popular in economics, but they recently, I think, have become more popular, and a lot of this is because of work that Raj Chetty as well as others have done, and they basically say it's a nice bridge between how you could use reduced form work, which can get really, really nice, clean, credible evidence of effects. You could get these nice, clean elasticities, let's say, and then take them into structural work to do policy simulations. And this use of sufficient statistics is now really, really popular in some fields in economics. The reason why it's getting popular is because in those fields where you're building these really, really complex models, where all the assumptions are embedded in footnote 26 in the 5th line of it, or in an online appendix 12, the way that you're getting these elasticities and different things is very, very transparent because you're using these ideas from that, be it a natural experiment or a regression discontinuity, whatever you like. This is why they become popular to a large extent, because they're really, really transparent. What I'm going to basically be arguing here is that I told you what a polygenic score is, or what it could be, depending upon which definition you want, but how we're going to build it and how it's being estimated, that model, that genome-wide association study, it's not that transparent at all. Again, questions welcome. I also talk fast, so the less questions I get, the faster I can talk. Okay, so this is sort of what a genome-wide association study is. This is how we do gene discovery. The only way I learned this is I collaborated now on a couple of projects where we do genome-wide association studies, and Mike was hinting at one of these yesterday, where we're basically taking some outcomes, some socioeconomic outcome, like educational attainment, and we're regressing it on lots and lots and lots and lots of genes. And the way we're treating the genes here is linear. How many risk alleles you have at this point versus how many risk alleles you have at that point. And then we put in some principal components to capture genetic differences across people. And then we have our random error term. What's in that random error term? Well, if we have a model about people trying to predict schooling, individuals are comparing the costs and benefits, they have lots of past information, there's lots of environmental factors, like is there an oil boom in Alberta? If so, maybe I'm going to drop out. Okay, all that stuff is thrown in the error. So this is strictly a genetic marker. And one way that you can predict what is a polygenic score is you can think about the predicted value for the regression from this is that guy. There are about 3 million SNPs that you could possibly have in a data set, depending upon how your gene was sequenced. Some data sets can only give you about 100,000. This all depends upon what architecture was used in your underlying data. The problem is that typically you only put about 3,000 genes in here, and which 3,000 genes you put in, it's somewhat random. There's it's not like anyone sits there and they say, I know these 2 genes are close by, I'm going to take this one, not that one. There's not, typically what you're putting in is whatever is most convenient. What you're assuming here is additive separability. It's a model that's linear in parameters. There's no gene-by-gene interactions. Because you're treating this gene variable as basically how many risk alleles you have, you're assuming linearity on the scores. It's not too hard, and this is something that I think economists have thought a lot more about, putting in dummy variables. Do I have A1, A2? Do I have A1, A1 versus A2, A2? Everything else, including things about our parents, all the variabilities in the error. Yeah.
This could be tested.
Easy to test.
Yes.
Yeah, easy to test. I guarantee you it'll fail. Because if you have 3,000 genes, you just do an F-test, I can guarantee. I know this from my own work because when I did early papers where I was using candidate genes as instruments, I would put in dummy variables, and then I could look at the effects. Definitely linearity failed in that world where I was only looking at 4 or 5 special genes. I guarantee you as it goes up, it's definitely going to fail. But this is basically how the CAN software that does this stuff, it always assumes linearity. No one, but no one talks about it. Yeah.
So if you,
Yes.
so do people like estimate different alpha K hats for each economic outcome they're trying to do, or would they say do a regression to understand educational outcomes and then use the same single polygenic score for each individual to estimate another economic outcome like wealth or something?
Okay, so historically they pick one outcome and they look at it in isolation.
Right.
But I think about 2018, trying to remember his name, he's a postdoc at Harvard now. He came up with something called MTAG, multi-trait analysis of genetic data. So now we can look at multiple outcomes together. And this has a lot to do with the fact of comorbidity, right? Because I'm obese, I'm more likely to be depressed. I'm also more likely to suffer from ADHD. So I'm trying to look at one gene in isolation on one outcome. I may be mistaking the effect of this gene on obesity when it's really due to a correlated outcome. So now there's just started in the last few years to have different outcomes and then looking at them jointly. However, still the game is, you have to pick which of these to put in. And what typically happens is that they basically try a whole bunch of different sets and then pick the one that has the highest AIC criteria. Which model, and that's the model that they'll stick with. Because you have so many, so you need really, really large samples to run this. So we look at really silly outcomes like educational attainment. Like, what does it mean to have, I'll do a very good Quebec example, 12 years of education. In Quebec, it means you went to CEGEP for 1 year. In Ontario, it means you're a high school graduate. Quebec would say that you're in a tertiary education. So that their educational attainment is just a pure quantity measure. There's no quality in there, and quality differences are large. But the reason why educational attainment is used is because in lots and lots of data sets, and lots of data sets where we also have the data on genetics. In order to do these genome-wide associations, we need huge, huge samples. Now, when I talked about how we're putting in all these different genes in, and I talked about how they're correlated with each other, you have basically the famous trade-off between, should I put this gene in? And if it's highly correlated, I'm going to have an efficiency problem. I may not be able to precisely identify one against the other because of multilinearity. If I leave it out, and that's the one that matters, I could be mistaking the thing for omitted variable bias. No one really talks about this, but all of this is going on in the background. So this is all, it's basically suggestive, and it's just purely association. Of course, you can never do a randomized experiment. We can't randomly assign genes, so this might be as far as we can go. In order to say that we have effects, we are making corrections for false discoveries. So the standard errors have to be really, really tiny, so we need really, really large samples. Really, really large samples basically means like 800,000 observations. So I've been involved in both the second and the third educational attainment GWAS, and we went from about 200,000 observations to about 800,000 observations. Now, when I talk about 800,000 observations, as a microeconomist, as most of you are, you think that means I have 800,000 rows in my data set. Here's educational attainment for Philippe, here's educational attainment for Lee, here's educational attainment for Myra, and there's all their genes. How many of you have done 23andMe? Nobody? Okay. Okay. So when you apply, I haven't done it, I don't want to know anything more about myself. But one of my co-authors has done it. When you sign up for 23andMe, you have to opt out of using your data for research purposes. So in one of our papers, we're using all the 23andMe data. So you might say, oh wow, what does that mean? It means you have 300,000 people. No, it means we get one row from 23andMe. 23andMe gives me the average educational attainment of everyone in their data set, and then the average for each and every single gene. And that's what's thrown into the regression, with a weight, because that observation has to count for 300,000. So some of the data that's used in this GWAS stuff is pure micro stuff. Other stuff is just averages. Can you imagine running a regression with like province averages for some outcomes, and then you have individual data for others? We already know, like from a long time ago, that if you estimate something with individual level data, you could get a totally different answer than you do with province level data. I think my favorite example of this is what is the effect of being an immigrant on language proficiency? So we do it with the US or Canada. So what do we think? If you're an immigrant, are you more likely to be proficient in English or less? Probably less on average. Imagine we do this with state level or province level averages. Well, immigrants don't sort randomly across Canada or across the US. They typically sort to places like New York. They typically sort to places like Ontario. They don't go to Mississippi. They don't go to Newfoundland. So if you do this with state or province level averages, you're going to get the exact opposite sum. So you really can't, this is what's called the ecological fallacy in political science. You can't take a relationship at one level and apply it to another level. But in this GWAS, the data is from all over the place. It's really, really messy. Now, I don't know how to interpret anything, but nobody cares. But this is what they do. This is just so people know. When we estimate these genetic effects, they're really, really, really small. On the one hand, this is reassuring to us because we really don't want a single genetic marker to have a huge, huge effect for many outcomes like educational attainment. This is kind of nice from the equality of opportunity standpoint. On the other hand, when these companies are selling you these products, they say, look at how great we are because we can use all this information about your genes, they're telling you that these genetic factors matter a lot. How much they matter depends a lot about what outcome you're studying. And I think there needs to be a lot more honesty in advertising in this area. So this is just showing you how the sample size has moved. So Dan Benjamin, who runs what's called the Social Science Genetic Association Consortium, he did the first GWAS where he combined many, many authors and many, many people's data to do this for educational attainment. His first one basically found that the polygenic score explained almost no variation when he had about 10,000 observations. Then he kept adding more and more and larger data sets. And the most recent data set is one by a guy named James Lee is the lead author on it. And we're now up to about, I think, 14% with a much larger sample, I think 1.1 million people. As we're adding more data, these things are explaining a little bit better. But as we're adding more data, we're adding more of these like aggregated data. I'm not really sure what exactly we're getting. So large samples is what's argued that is what you need. They're doing a bit better. I don't know exactly what they're identifying. The other thing which I kind of like about this paper, Oppe and company, and it was in Nature, was that we estimate the data with 80% of the samples. And in there we found 76 genes matter. And then we actually went out and tried to predict in the remaining samples, do we find the same 76 genes? And we actually found it was 74 of them. So this was somewhat reassuring. But at the end of the day, we're only explaining around 6% of the variation. All the educational attainment GWASs that are in HRS, AdHealth, any microdata set are coming based on the Oppe and Al calculations. And the Oppe and Al calculations are based on all the SNPs in their model. And one of the big challenges in the HRS, why I'm having a hard time reconstructing it, is the SNPs in the HRS are predominantly imputed. They're not the actual ones, because in the HRS, when they basically measured people's SNPs, they measured different SNPs. They measured different genes. But they know that this gene is close to that one, so we'll guess that you have this one. And that's what they're doing. So this is just stuff to keep in mind in the background. So in case anyone reads my papers, I've had concerns for quite a while. I think what's new and what I thought about over the last year, where my new concerns really are coming, is that when you think about pooling data from many studies, this is kind of like meta-analysis, which is a very, very popular tool in the medical community. It made a lot of sense in the medical community because you had randomized control trials. So you could easily pool data sets together because what the variable you're interested in was randomly assigned, so there's no omitted variable bias. Here, you're pooling together observational data. And observational data is predominantly not coming from random samples to begin with, because people have to self-select whether or not they want to provide a pupil swab to 23andMe. So Steve Slavin, who's an education researcher, basically defined meta-analysis as an exercise in mega silliness. I'm not really sure if this is the right way we should be thinking about how to analyze genetic data. We need to think a little bit more about coming from it. I talked about this a little bit before. Because of confidentiality concerns and privacy, which is important, I'm sure others will talk more about it today, we don't have individual level data, or we're not provided with individual level genetic data in many data sets. We're provided with averages. We have to be very, very careful and think carefully about what we can learn when we're using averages. I talked a bit about one of the big challenges is that when we were using these genome-wide association studies, and we're not using the real SNPs, but we're using implied SNPs, we don't really talk about that. Should we treat it the same way? Should we talk more about measurement error? Should we say, maybe this is an effect that's biased downwards, maybe it's larger? We need to think a little bit more about it. This fourth concern is something which I think I think it's a bit more important. It's when people are trying to say that a gene is significant in a genome-wide association study, they're testing what's called the moment condition in the IO literature. That's just a fancy way of saying the alternative hypothesis is not equal. So is there a difference if you have this gene versus that gene on a bad health outcome? I really think what you want is a functional inequality, a one-sided test. What you really care about when people talk about polygenic scores is this gene increasing your odds? You may say something is significant, but maybe decreasing your odds. And then you're adding it with everything that's increasing. I don't know how to interpret this thing at the end. So I really think that there needs to be a big movement towards testing functional inequalities with multiple testing. I've been thinking a lot about this with Kevin Song at UBC. And this is something which I don't think people think deeply enough about. So I'm going to talk a little bit more about some of my older concerns in the coming slides, and I'm going to relate this back to personalized medicine, so Philippe isn't mad that I talk all day about polygenic scores. So he's happy, okay.
I'm easy to please.
Okay, good, okay. So you have, I think there's two types of studies where polygenic scores are used. The first is something which I thought about way back in 2003, and I got roasted on, was using genes as instruments. Suppose we're trying to estimate the returns to education. This is something labor economists care about way too much. Maybe we're going to use our educational attainment score as an instrument for how many years of education we get. That's one way. Another way is we could use these polygenic scores as control variables. So yesterday, Mike put up a slide where he was citing work by Barth, Papa George, and Tom. That's what they're basically doing, is they're going to throw in this educational attainment score right into a regression. And of course, they're going to throw it in there, assuming it's measured perfectly. There's no discussion about estimation. All these studies, when they're doing this, even as an instrument, you're sort of ignoring the fact that this guy's estimated. And there's a whole big literature in econometrics about using generated regressors. You have to fix things up. What I want to do is I want to contrast, if you actually think about what this is, and into these models, what are you actually assuming? And should you use a single gene or a couple of genes on their own, or should you use these polygenic scores? And I think the movement in the literature, and lots of my friends like Dan Benjamin and David Cesarini are really pushing strong on using polygenic scores. I'm now starting to do a bit of pushback, and hopefully I can convince you this is not crazy to push back. So, and now this is the slide where I changed my mind on this morning. So a potentially good application of polygenic scores could be, maybe you should use this for an IB application. So here I'm going to use the polygenic score as an instrument for years of education. The nice thing...
Do you have a weak instrument problem?
So here, because it's the polygenic score, I don't have a weak instrument problem because it's all these genes together. It's going to have a strong first stage relevance. When I use the individual genes themselves, my first stage is usually on the border of being weak, if not weak. So these individual genes, because they have very, very small effects, this is how, and I've done papers about this, and I've gotten roasted afterwards. Individual genes themselves as instruments, the first stage you can barely survive, but this stuff you do fantastic in the first stage. So when I first typed this up, I thought this is a great idea. Then I said to myself, hold on. If this score is a function of 3,000 different genes, implicitly, so people who do this, they say I have one endogenous regressor and one instrument. I'm just identified. But really that instrument is a function of like 3,000 regressors. I got into trouble when I was just looking at 4 genes, no one believed my exclusion restriction. With 3,000 instruments in there, I think there's no way the exclusion restriction passes. So this is where I say, like, on the one hand, the polygenic score can help you because it has more explanatory power. On the other hand, you could be into a lot of trouble because the assumptions you have to make about exclusion are just very, very high. And not put differently, the way I wrote it down here is that if I put my first stage as all of those genes, I would have what's called the many instrument problem. Because I have lots and lots of variables with very, very weak correlations. But the nice thing about the polygenic score is then I could sidestep defending the exclusion restriction assumption, because I could just say, look, I'm just identified. I don't think that's a good thing. So I think be very, very wary. But this is, I think, the best case use of a polygenic score. Like the type of work that's being done now where it's being thrown in as a control variable, I think is much worse and all motivating. To get to my next slide. So this is like a lot of papers that people are doing nowadays where they're basically saying, I'm interested in what is the effect of these genes on some type of socioeconomic outcome like wages, and maybe are there differences in some environmental input based on this score. So people use these to basically say, I really care about is estimating gene-environment interactions. So I'm going to get this score, and the reason why I'm using EA score here and not EA hat is because EA score is usually just this thing. That stuff's not thrown in there. So it doesn't matter how the polygenic score is calculated. When you do this and you're treating the data as if this variable is measured perfectly, everything is off. So at a minimum, researchers have to say, this is a generated regressor, even though the HRS doesn't talk about it, because it's a generated regressor, none of your estimates are consistent. So I'd be very, very cautious about using it. This is the first thing. I've lately been seeing a lot of papers where people now try to say, well, there's many ways to estimate polygenic scores. I'm going to use one as an instrument for the other because they might be measured with error. I think the measurement error problem is a second order concern. But I have a bigger issue with this type of research, which is going to come up in, I don't know, 1 or 2 slides. Where I think we can actually gain from machine learning is, because we have so many genes down here, we could use something like the lasso and say which are the genes that matter, and then use that as a data-driven way to explain which genes we pick. So I actually think, and I'm going to talk more about this coming up, from a personalized medicine standpoint, how we analyze genetic data, when we care about polygenic scores, we're caring about predictions. I think using some machine learning tools will help us quite a bit. I'll get there. What I am proposing nowadays, what I think is the best thing to do is, why don't you just estimate the reduced form? Right? Because basically, my wage is a function of this polygenic score, and why don't I just put in, I can substitute in that whole first stage into that second stage, just estimate the reduced form. That's clean. And you have to also understand that when you're getting these weights on these polygenic scores and you're pooling data from different places, you don't really know if the effects are really coming from the data set you're analyzing or from other sets. Okay. The other thing which I thought a lot about is maybe another way to use polygenic scores is just basically create dummy variables. Is my polygenic score above the 75th percentile or below the 25th percentile? That might be a safer way to use this data. I think treating it as a continuous regressor is highly problematic, especially given how it's constructed. There's a bit more about machine learning stuff. A lot of machine learning stuff does really, really well if your data is homoscedastic. I can talk more about that over break. You
have 6 minutes left.
I have 6 minutes left, and I have 4 slides. Okay. Okay, so what we're trying to do here is we're trying to think about, if we go back in time and think about twin studies, we were trying to basically trying to understand by comparing monozygotic twins, how much is heritability, how much is environment. All that environment stuff is implicitly thrown in the error term in the educational attainment equations. So when Barth and company are taking an educational attainment from a regression, which basically say genes have an effect, but they're totally orthogonal to environment, and we're going to take that predicted effect, throw it in the second stage regression, wherever it is, up on the previous one, and estimate gene-environment interactions, there's a lot of tautology there. You're estimating something saying there's no gene-environment interactions to identify gene-environment interactions. It doesn't make any sense to me. And I've talked to them quite a bit, and Kevin said, I know how to solve the problem. I'm going to write the paper for macroeconomists, so I won't run into you as a referee anymore, and that seems to be working. We'll talk more about macroeconomists too soon. Okay. So this is one of the things when you're pooling data from different sources. I think you have to take into account that it's not just the populations differ and you have to control for principal components of population. You also need to think about how the environments differ. I call this environmental stratification, going back to a paper by Niels Rosenquist and company. The other thing which drives me crazy in this literature is that people abuse terminology like crazy, and especially in the genetics as instruments literature. People call genes as instruments, especially in epidemiology, Mendelian randomization, as if which gene you get is random between across the population. It may be random in between dizygotic twins. I like to call that a genetic lottery. But otherwise, this is just encouragement. These genes are they're not destiny. They're just maybe encouraging you to do stuff. And basically, you inherit your genes from your parents, who inherited from their parents. Dynastic effects probably exist. So people like to call this Mendelian randomization, because every time someone hears randomization, they relax. I don't have to worry. I really think that this is abusive and cheating, but okay, that's it. So the other thing I mentioned before, when we talk about genetic data and how we're analyzing it, you can't randomly assign genes. There's just simply associations. The effect sizes are always going to be small for most of the outcomes we care about. From a social science standpoint, this is reassuring in a lot of ways, but from a health standpoint, this could also be a concern if people are trying to convince you that the product that they have is important. Of course, if a gene really has a big effect, like in Huntington's or in inherited retinal disorder, that's important to know. We have no idea exactly how these genetic factors operate. We're basically not even modeling it. Like that first stage that GWAS, there's no model there, it's just pure association. Then we have our good friends. So even though we're not modeling it, and there's lots of concerns about things like privacy or are we violating individual rights, I don't think that we should be afraid to analyze this data. And this is the point at the bottom here, is that macroeconomists have no problem to keep doing research on poorly understood phenomena. And I don't think we should have any problem to look at genetic data. Like, this is still in its infancy, and we should go in and do work in this area. I thought that was a safe comment. Lee, you can keep it to the team. I have tenure. Okay, all right. I think that they are a nice way to start to think about individual heterogeneity. Putting a fixed effect in is kind of unsatisfying to me. So I think that there is some advantage to using this data. We just have to figure out what's the best way to do this. And this is where all the work on personalized medicine is going to come in, because as we improve our understanding, we can start to develop better treatments. But in order to improve our understanding, we actually really need to at least not let the statistical geneticists run the show here. We have to basically come in and think a little bit more carefully about how the models are written and what they are actually implying. I think that there's some different research designs where we can get better data, better variation. From a personal medicine standpoint, so I thought about this quite a bit, because again, I think the goal is we want to know which gene matters. And when we care about that, we care about prediction. And when we're caring about prediction, there's these methods called regression trees, which we know are very, very unstable if the data changes a little. The whole structure of the tree can change dramatically. So Leo Brayman came up with this idea of bagging, where you're going to create bootstrap samples and build these trees over and over and over again. And this was supposed to be a big, big improvement, but there was a big problem discovered with bagging, which is that if you have a very, very important predictor, all your trees may look the same because they're always splitting on the first variable at the beginning. And to me, that's exactly what we sort of want to know, is if we have a genetic marker that really matters, we actually want these trees to be sort of correlated. We want to use bagging to see if they're always splitting at the same place. If so, we should be a lot more confident. Yeah. So to solve bagging, he goes to random forest. We don't want to go to random forest here. I think bagging might be a very, very useful tool on how to analyze this genetic data. And the beautiful thing about regression trees are they're completely non-parametric. We're not modeling things. And they're going to look at every single split point, and they're pretty fast. So summing up, what I wanted to get across is automated sophistication is just a fancy way of saying having canned software to do our genetic genome-wide association studies or build polygenic scores is non-trivial. When people go about doing these studies, it takes a lot of work to convince people to share their data. Lots of attention goes to that, but then you just throw the data into canned software. And I think that this canned software is problematic because the assumptions that people are using when they're creating these models, they're not explicit about it, and I think that this is very, very important. Something which I've been trying to do over time has been trying to reduce the barriers to entry by trying to classify or trying to demystify the jargon that people use. I can't remember who I was talking with yesterday. One of the challenges, even within economics, moving across fields, is you have to learn the special jargon across fields. Learning this jargon across disciplines is really, really tough. But I think this is, I'm always happy to answer questions by email. I think we should not, I think even though it's poorly understood, we should be using this data. It's a new data source. I think genes are important. They're going to have lots of big impacts on policy guidance. And I think we have the potential to design new effective approaches to improve societal outcomes. But I think we should be basically more involved at the data analysis stage. And I think that what we're really, and this is where I think the health guys are way ahead. I don't think the question we should be after is, does a gene affect an outcome, but does the available evidence suggest that a policy that targets that gene, will it pass a cost-benefit test? I think that's the question that we should be asking. And the last point that I want to make clear is, we live now in an era where everyone is so fearful of everything, and individual privacy, all of this. What is Facebook going to do with our cookies? Are they going to sell our information? I think the only way we're going to make real progress here is if we can also convince society that there's a healthy relationship with researchers analyzing this genetic data. Right now, I think it either goes really to the two extremes, and I think we just need to sort of educate people a lot more so they're more confident that we can use this data, so they'll provide this data, especially at the individual level, and then we can provide better evidence. And I think this is something which we can call public education is going to be very important.